So thank you for coming. Today we are very happy to have Professor Prateek Bansal from National University of Singapore. He's a presidential young assistant professor. I know Prateek for several years now, so I'm very impressed by his work. And we're very happy to have him here. His basic PhD is from Cornell University on transportation with a minor in statistics and economics. But he's doing a lot of economics work, so today you will hear about that. He's a master's from UT Austin, and then he's an undergraduate from IIT Delhi. So he is, maybe he'll give you like a very brief description of what he has been doing, because it's a little bit different than for what he was doing for his PhD. But again, we're very happy to hear him talk about some very cutting-edge research. And feel free to ask him questions. Don't be like you are in my class. Be quiet. Don't be quiet. No grading, nothing. Ask him questions and try to learn from him. Thank you, Prateek.
Thank you, Khan. Thank you for inviting me for the talk. So today I'm going to talk about. Let me just reduce the screen size first. So today I'm going to talk about basically how do we generate the spatially heterogeneous synthetic population by combining the household travel survey data sets and a lot of passive collected mobility data sets that are emerging in last, I would say, 5 to 7 years. Okay. But before starting that, what I'm going to, I'm splitting my talk in 3 parts. In the first part, I'm going to talk about the feasible and diverse synthetic population generation. And the idea of this part is to really give the sense of what do we mean by feasible synthetic population and the diverse synthetic population. And also in this segment, I think everyone will also understand what synthetic population really means. And in the second part, I'm going to really talk about how do we combine the household travel survey data and the cell phone data to generate the synthetic population with the socio-demographic attributes and the home and work locations simultaneously. And the third part is ongoing, which I'll just touch upon depending on how much time we left, how many questions you ask in the talk. And if we have more time, I'll touch upon the third part, where we are combining the household travel survey with the smart card data to simultaneously generate not only the synthetic population, but the activity locations as well. So if we get started with the first part, the idea of synthetic population is basically we try to mimic what we have in the actual population. We try to generate the synthetic agents in the computer which have the same demographic characteristics that you have in the actual population, right? And after that, we generate their activity patterns. So if you think in a broader terms of the travel demand forecasting framework, then activity generation is the one part and synthetic population generation is the another part, very important part. So in this part, we will be mainly focusing on the synthetic population at an individual level. So just to give you an idea, in terms of the existing methods for the synthetic population, what we have is this is the basic initial method, which is the iterative proportion of the fitting. And these are the 3 other methods, which we call the simulation-based methods. I'm not going to talk about them in detail, but mainly we'll give you an idea of how we generate the feasible and diverse synthetic population using these simulation-based methods. So before we get even started to the advanced stuff, let's first take an example of what we really mean by synthetic population generation. So in general, the data that we consider, let's say there are 2 variables, x1 and x2, and x1 can be, let's say, gender, maybe male and female. Male is 1, female is 2. x2 is age, let's say 1 is the younger person and 2 is the older person. So we observe this information that you have in the micro data through any, let's say, survey sample, okay? And you have some totals for the x2 and x1, which basically you have the marginal distributions, and you use the IPF to fill these IPF to actually extrapolate the distribution, right? But basically there are mainly 2 problems with this simple approach, and it is important to understand those 2 problems if we really want to advance the methods to generate the synthetic population. The first problem is, let's say we had some other category, basically let's say someone who doesn't specify the gender, or let's say very old category in the true population, but we don't observe that in the household travel survey data set. Then if you generate the synthetic population, your synthetic population will never have that category because your sample didn't have that specific category, but the category is there in the population, right? So we call it a zero cell issue. I'll talk about this issue and how severe this issue in a minute. The second issue is the it's going a bit slow. Let me see if there is someone saying something in the chat. Okay, great. That's fine. So the second issue is the scalability. If you have too many attributes, then running IPF is very difficult. It's not working very smoothly, so let me just use the okay. So the zero cell issue, to understand the zero cell issue, what we do is we combine the household travel survey data of South Korea for 2010, 16 and 21. So what you see, we call this as an H population. And what we do is from this H population, we take the different proportion of the samples. So on the x-axis, you see the sampling rate, basically 0, 10%, 20%, 30%, 40%. On y-axis, what you have is the two things. The percentage of the attribute combinations and the percentage of the data instances that you actually sample in those at the different sampling rates. So if you look at traditional example, when you sample only 5% of the data, when you sample 5% of the data, you only capture 11% of the attribute combinations that you have in the population. And I'm talking about when you are taking the representative sample. So in terms of joint distribution, we only capture the 11% of the attribute combinations. However, they represent the 56% of the population. So this 11% is a very important number. We want to increase this number using these generative modeling techniques because they can generate those attribute combination around the sample distribution that we have. Okay. So that's why some new techniques have been introduced to generate, little bit out of the sample, not just the combination which are in the sample, but maybe something surrounding the sample as well. So the two common techniques for doing that in the past was GIF sampling and the Bayesian networks. We are not going to talk about it, but just for a reference, you can see that these are the two common techniques. So we can understand from now here onward, like we understand that, okay, we have the only 10% or 11% of the population attribute combinations in the sample. So how do we increase it? So if you look at this figure to understand the concept of the sampling zeros and the feasible zeros, is very important to see how these simulation-based methods work. So if you look at the population distribution is in the red. The circle that is in the blue is the sample distribution, and circle in the black is the generated distribution. If you're doing the IPF, then this red circle will overlay on the blue circle because you are generating exactly same attribute combinations that are there in the sample. If you're using any generative model, then you are going to generate this black circle, which is slightly different from your blue circle. But now we need to understand mainly these 2 points. So if you look at this point here, this point is in the true population, right? And also in the generated data. So it's a feasible attribute combinations that we have generated. But if you look at this point, it has been generated by this generative model, but it is not observed in the actual population. So what is the example of this? It may be, let's say, a child with a graduate degree. You can generate such a respondent through generative model, and that's where the problem occurs. Okay? If you generate the infeasible zeros. So generative models are all great, but you also generate some garbage. Okay? So the idea is, how do you handle this garbage? So what we did, and before I get to so I think the point is, we need to maximize the visible zeros, but minimize the structural zeros. Okay, this is the main idea if we want to generate any synthetic population. Now, if we move forward, and these days deep generative models are used a lot to really generate the synthetic population. So what we do is, I'll just talk about the main thing that we did to increase the feasibility of the population and reduce the invisible zeros. What we do is we add a regularization term in the loss function of GAN and VAE. So the loss function that we design is so the hypothesis is the sampling zeros distance to the boundary of the entire training sampling distribution is shorter than the structural zeros. So you can check this hypothesis here. So sampling zeros have smaller distance compared to the structural zeros on an average. Yes?
Why are you trying to maximize the sampling zeros?
Because any agent-based model, the idea of agent-based model is you want to mimic the population distribution, right? If you have only fewer combinations of the population distribution in your agent-based model, it is not heterogeneous enough to represent all possible changes which are happening in the population. So you want your synthetic population to be as heterogeneous as possible. So that's why you want to have more attribute combinations in your synthetic population. And the only way to do it is to actually expand the sampling zeros and really increase, basically get as much as from this remaining part of the bowl which we don't sample. So this is where the generative modeling helps. But as we said, we also come up with these structural zeros along the way. Okay? That's a great question. Yes.
So if I understand correctly, you won't be trying to fit that blue sample distribution. No more.
Exactly. Yeah, that's the main idea. So what we do is, right. So what we do is we add the distance to the boundary of each generated data to the training data, okay? And add as an additional term to the GAN and VAE loss function. We don't do anything fancy, we just use the inclusion and add this term to the GAN and VAE. And I'll briefly present the main result that we obtained. So there are two things which are important to understand is the diversity and the feasibility. The feasibility means the proportion of the attribute combinations that we generate that are there in the actual population. And the diversity is basically the number of combinations that we are generating. So if you look at the sampling from HTS data, which is very similar to a version of IPF, you can see where you're just drawing from the blue circle, then the number of combinations that you generate is 30,387, and you have 100% feasibility because you are generating from the sample data. So all those are there in the actual population. By the way, I forgot to mention one thing. This is more of a thought experiment. We never observe the full population. So we are assuming the HTS as a full population, and we are taking sample from that to just differentiate so that we kind of already know what is the true population. Okay? So we are just doing the true, we can't compute the precision in the real life because we don't observe the full population distribution, but we can still have sort of through this thought experiment we can do it. If you use the Bayesian network, you can see you can generate 10 times attribute combinations by just generating around that blue circle. But the precision is 73%. Basically, that 73% of the data that we generate is in the actual population. So we tried the vanilla VAE and vanilla GAN, and vanilla GAN is giving a little bit better precision. And but as soon as we introduce this basic loss function, we are able to increase the feasibility to the 89% in GAN. Okay, very basic, very simple idea, but we are able to improve the feasibility. But one thing to note, the diversity decreases significantly. Right? So there is a trade-off between the diversity and the feasibility, yes.
Excuse me, how do you evaluate that the generated sample is in the population and not in the sample in a real case problem?
In the real case problem, you cannot. it is just a way to add, just way to evaluate. You can you can tune these models by assuming your sample as a population and take the subsamples from that. You tune your model by considering your sample as the population and taking samples from that, and then use those hyperparameters on the entire sample. So that is the way to do it. There is no way you can do it in principle. Okay, thank you. So this was just to give an idea of what we mean by the feasibility and diversity and what synthetic population is. Yeah.
Sorry, can you go back to the visual?
Yeah.
Which of these, so my kind of concern would be you might be oversampling the really rare cases in your model, right? Like a 18-year-old millionaire, for example. Which of these metrics are evaluating that component? Like the frequency of each type of person corresponds to the actual distribution.
So this is exactly evaluating that. Let's say you are generating 100 agents.
Yeah.
89 of those agents, the attribute combinations that you are getting for those 89 agents are there in the true population, which are in the black circle.
Yeah, if it exists, you get like a positive score there.
Yeah.
But if you overestimate...
If it exists in the black circle, then you get 1.
Yeah.
If it doesn't exist in the black circle, then you get 0.
Right.
So 89% of them exist in the black circle.
So so that's my point. Like if you estimate there's 100 18-year-old millionaires in the data set, but there's only one.
Oh, so the marginal distributions, right? You mean the marginal distributions on each variable. I don't present these results for the marginal distribution, but the marginal distributions are very well. For example, these are the results of the marginal RMSE. So this is exactly related to the marginal distribution. So obviously, if you use the very simple household, like the IPF type of a model, then marginal distribution is very well represented because the RMSE is quite low. So you compromise a little bit on the matching the marginal distributions while you use these generative models, but the compromise is not so significant. Yeah. Yes.
How do you avoid the overfitting problem, and what metric do you use to
Sorry?
what metric do you use to evaluate overfitting problem?
For the fitting problem.
Overfitting problem.
So
you just memorize the whole data set instead of you generate new samples.
So why do you think here you will face the overfitting problem?
You just use too many.
Because we are not doing the prediction here, right? We are generating the population. So you can check whether there is an overfitting problem or not by looking at the marginal distributions. And it's okay to overfit in this case because here you want to generate from the population as well. If it was a prediction problem, you are right that we don't want to have the overfitting. But it's not a problem in this case.
But you have a privacy concern.
That's entirely a different topic. If you get to the privacy concerns.
The original data set. I mean, you don't want to leak any information from the original.
But you can't handle that issue by looking at the overfitting problem. That issue is a very different problem because even if you observe the true population, right, there can be a privacy concern. Even you generate a sample, then also can be a privacy concern. So I don't think you can handle the privacy concern in this using just generating the synthetic population.
Okay.
Yes, if you're thinking about injecting the noise into it and then making sure that if someone combines this data with the other data set, we still don't identify the respondents, that's, I think, a very different problem altogether.
I see. Thank you.
Okay. Yes.
So I wonder, so because I guess the thinking is that, okay, you get a sample from the population with a certain sample size, and then you can perform this, right?
Yeah.
What happens to the precision as your sample size
Increases. It does improves. It does improve significantly. I don't have it here, but it might be like a 5% of the sample, but it does improve significantly as you increase the sample size. So this is a very good question because that tells us that how much sample size do we really need in the household travel survey data set. So when we presented this to the Land Transport Authority, they were also interested that as the sample size increases, how we are able to improve the precision or the basically feasibility. So I don't have the plot here, but in the paper, I guess we have the plot where we show the different samples and we show how the precision increases. If it is not there, then I'll be happy to look at it. Yeah, but we do have that. That's a good question. Any other question? But I'm glad you are asking questions. Great. So let's go to the main topic now. This is the paper which just got accepted last year, already last year, that was 2023. So let's talk about the main topic, which is about how do we use the cellular data to generate the spatially heterogeneous synthetic population, basically a synthetic population with home and the work locations. So as we have been talking about the home and the synthetic population, we were focusing on the only age, gender, and income, right? But home and work are also very important component because they are the anchor points for the all other activities which are happening. So in this work, let's say we want to understand how do we generate the home and work locations along with the socio-demographic characteristics together, okay? So we need to understand why we can't do it just using the household travel survey data first, right? Before we think about even combining the cell phone data with the household travel survey data, we need to think why we can't do this with the household travel survey data. So if you think about the major issue is you have a small sampling rate, like you have 1 to 5% of the samples, and that's why you have very few home and work locations. If you really want to generate the home and work location distributions which are heterogeneous enough, then you need to generate the conditional distribution of the home and work location, which is conditional on the demographics, right? That distribution you can generate at a very less resolution. But if you go to the very fine resolution, then you will have very few entries to generate that distribution, right? So that's why household travel survey data is not very suitable to actually generate the home and work location and the socio-demographic simultaneously. So generally the process these days is we generate the socio-demographic and we use some heuristics to assign the home and work locations to people. But what we are claiming is if we use the cell phone data along with the household travel survey data, we can generate both of them, the household home location as well as the socio-demographics together. So let's first look at what we gain and what we lose when you use the cell phone data. So if we look at the household travel survey data, generally we have the 1 to 5% of the population and we collect it at 3 to 5 years. With the passively collected mobility data, it can be smart card or the cell phone data, but what we have is around 35–50% of the population. We observe very frequently every day. And what we have is the socio-demographic characteristics and the household travel survey data, but in the cell phone data we have very limited ones. And we don't have a lot of information about the travel mode and activity purpose in the cell phone data, but we do have all that information in the household travel survey data. So in summary, what we can see is, well, cell phone data has very interesting, very high spatial resolution, but it doesn't have the many socio-demographic characteristics. Household travel survey data is a small sample, but it has all the characteristics that we want. So there should be a way to combine these two data sets so that we can, yes?
What is the actual origin of these cell phone data?
So cell phone data is shared by the telecom operators in an aggregated form. So they have the data of the movement of the peoples and they use the triangulation of their towers, and based on that they identify the location and they provide it at a distribution level or sometimes at an individual level, but they are fake individuals which represent the distribution that is there in their data.
Is that a specific arrangement to South Korea or something like that exists here in the US?
It exists in Singapore for sure, it exists in Korea, Australia for sure, and I think Singapore as well, and in the US as well in some parts. I'm not sure about the US, but I know about Australia, Singapore, and South Korea. Yeah.
You mentioned it was aggregated. What can you?
Yeah, I'll talk about that in a minute. Yeah. Okay. So I'll talk about the data in a minute, but the main issue is, as we have seen, the dimensionality of the spatial attributes is also a lot in both HTS and PC data. When we are combining, that's also one of the concern, and the mismatch of the location combination. But let's look at the data first, how it looks like. So what you see here, you have so what we present here is only the spatial distribution, basically proportions in the units at a spatial scale. We have the 400 grids, and what you see around is the PC data proportion. So circle size is representing the proportion, and the full circle as well as the hollow circle are both representing the HTS and PC respectively. PC I will be using a lot. PC is passively collected mobility data. So we see that the spatial distribution is very similar in both terms, but if you look at the number of combinations that you obtain in the household travel survey data is around 8,000 home work location combinations, but in the PC data the number of work location combinations that you get is around 14 times, around 110,000. So and if you look at we give the index to each of you can say zones or the spatial units, and if you look at the distribution of the home work locations, you can see it's quite dense in the PC data compared to the HTS data. So let's define some notations which I'm going to use, and let's look at some of the characteristics of the HTS and the PC data. So before we think about the fusion, it is important to look at some of the characteristics of the HTS and the PC data. So we have two characteristics, gender and age, and we derive the commuting distance from the data that they provide us. It's an individual level data that they provide us, but without any other information apart from age, gender, and the commute distance. And if you look at the gender and age distribution, it is pretty similar in the HTS and the PC data, and even the commuting distance distribution is not too different. So we define the social-demographic attributes, which are only in the HTS data, we call them X. The social-demographic attributes only in Y, which are common in both HTS and PC data, we call it Y. And the common spatial attributes, which is the home and work location, we call it Z. Okay? And in terms of the data set, we have around 3 million individuals in the PC data and 8,800 individuals in the HTS data. So if you think about the data fusion problem, so if you think about the data fusion problem, what we really want is, if xi, yz, gh, we define it as a fused distribution, we want to minimize the distance of this fused distribution with the HTS data as well as the PC data. That's the main thing we want to do, right? So you can define any probabilistic measure of distance. In this case, we define the Jensen-Shannon entropy. You can define Taylor divergence, any other different measures of the probabilistic distance. So here, what we are defining DJS HTS as a probabilistic distance between the two distributions that you have in the HTS data and the fused data. One thing to note there, when we are writing for the PC data, which is the passively collected mobility data, we don't have X here because X is not available in the PC data. Right? But if you directly start solving this problem, then it's a very difficult problem to solve because you have too many attribute combinations, because you're considering the at home and work location also as an attribute and the realization of the attribute. So if you think about the probability mass function, then it's you have basically many points on which you need to put the probability mass, which is 1 point times 2 raised to power 9 in our case. So what we do is we think about the cluster-based, we do some clustering and play with the probability distributions to simplify this problem. So the first step of simplification is we start thinking about creating the geographical clusters. So what we do is we just create the cluster which are at the geographical level, where you can have the both observations in the PC data as well as in the HTS data. We'll talk about that, how do we decide the number of clusters and how the number of clusters affect this matching. But for the time being, we just first start with a cluster. And obviously, if you increase the number of clusters a lot, let's say in this case we have 1,000 clusters, then obviously there will be areas where you will not have the HTS data, right? If you increase the clusters too many. So this is just a more general situation when we work with some, let's say, we will formulate for a general number of clusters, and we will see the properties as things as we move forward. So what we do is, once we have defined the clusters, geographical clusters, we break down this fused joint distribution as using the law of total probability first. We are just using the law of total probability on the CK. After that, we do some manipulations which I avoided here, which are just the probabilistic manipulations, which you can find more details in the paper. But what we get is the fused distribution we get in terms of the joint distribution of the xi, yj, ck, yz, zh, and ck. Remember, zh was the spatial work and home locations, and yz and ck fused. Okay. Now, one thing which is important to note here, if you look at these two terms are available in the both HTS and PC data. Only this is the term which is not available in both HTS and PC data, right? These two distributions can be found in the PC data and the HTS data. So what we do is, because we already know these two distributions in both HTS and PC data, we say that it's the modeler's responsibility, or modelers thought about the reliability on the both data sets that they have for the HTS and the PC data. So we say that this can be a linear combination of the attributes that we are generating, linear combination of the probability distributions in the HTS and PC data. But the trick is, how do we work with this, the fused distribution? Because this fused distribution is the xi, yj, and ck are there, and this distribution is only available in the HTS data. But, so you want to minimize the distance of this distribution with the household travel survey data, but at the same time, you want to have the joint distribution of the yj and ck like you have here, because this is the fused distribution you have defined. So while minimizing the distance of this joint distribution with the HTS data, you want to preserve this distribution, just to have the consistency at all levels of the distribution. Okay. So to do that, if you simplify this problem really becomes that this xi, yj, ck fused distribution should have the minimum distance with the HTS data, but we have to maintain that the joint distribution of the yj, ck fused should be consistent with what we considered here. Okay. So if you think about this, what we can do, it's a very low dimensional problem now, because you have for any given yj and ck combination, you can solve for the all attribute combinations of the xi. So the problem which was I cross j cross k decision variables, this becomes a j cross k problems with the I decision variables. And I is basically the number of attribute combinations for the x, j is the number of attribute combinations for y, and k is the number of clusters. Okay. So one thing which is important here, when we are doing these combinations, we are applying this linear combination on ck, but we were worried whether this property will transfer to the yj and zk joint distribution or not, because we are not interested in the joint distribution of yj and ck. We are interested in the distribution of yj and zk, which is the actual observed distribution of the spatial home location combinations and the common socio-demographic attributes. So just to recap, what we are doing is we are minimizing the distance between the fused distribution and the HTS data, conditional on maintaining the joint distribution of the yj and ck. So if you want to see it in a framework form, we have the spatial attributes, we do the clustering on that. The clustering gives us the joint distribution of the yj, zh, ck, and yj, zh, ck. We apply that linear combination, and that gives us the fused distribution of the yj, ck. Now we have this xi, yj, ck, HTS. We want to create the fused distribution from that, but we want to condition on this yj, ck fused distribution that we have already obtained at the lower level. And once you have this distribution, fused distribution, we already have this, you can generate the joint distribution from that. So let's see,
Prateek,
yeah.
do you make an assumption on the type of distributions?
No, it's non-parametric. We don't make any assumption, we learn non-parametrically.
it won't preserve any item.
Yes, we don't take any assumptions in this. Yeah, so I'll show you the some properties and the results, and then we can talk about the other. Yes.
Excuse me, what was the idea behind linear combination?
So the idea is as follows, like these two components are already there in the household survey and the PC data, right? So we were thinking that is it really an optimization problem? It is not really. It is more about what data you rely on more when you have the board distribution in the board data set. So that's why we didn't unnecessarily optimize the part of the problem which is not required to be optimized. So that's the reason if you rely that the joint distribution of the YZ-ZH is more reliable in the PC data, you put alpha equal to 0.9 on the PC data and you put 0.1 on the HTS data. In our case, it's not even a problem because our HTS and PC data have very similar distribution for the Z and Y. So you will see that alpha value will not change a lot of result in our case. But if the joint distribution, if the distributions of the common social demographic attributes and the spatial home locations is very different in both data sets, then I think we have to make a judgment that which data set is better. And I think this alpha is a judgment that how much weight we put on the reliability of the information that is there in the data sets. So that's the intuition behind that. So one thing that I was talking about, that we put this linear combination on the Yj and Ck, but we want to transfer this information for the Yz and Zh. So we can derive the sum properties and we can show that this joint distribution of the Yz and Zh also, if we use this whole formulation, we end up with this property also holds for the joint distribution of the Yz and Zh. So you have the proof in the paper, which I'll provide the link later. The another interesting property that we can say that if alpha equal to 1, then this joint distribution of the Yz and Zh is equivalent to Yz, Zh, HTS, and when alpha equal to 0, it's equivalent to PC. So this is what also you can show by doing this. And one more reason that we wanted to have this alpha here, it is related to the feasibility, right? Whatever the attribute combinations that we are generating, they are somewhere in between these two data sets. We are not just generating any attribute combinations for the common social demographic characteristics or other. Okay. So let's look at the results, and I think that will give more insights of what's going on. So what we do is we have the Seoul population is around 12.5 million. We have the PC data 3.05 million, HTS data around 8,000, which is around 0.3% of the population. So what we do is we combine those and we generate the synthetic population, and you can see the maximum here is the 3 million. Okay.
So are these unique measurements for the PC data?
Yes, unique measurements.
So you don't have the same person twice?
That's a unique measurement. I mean, the same person may not be twice because, I mean, if you think about the home and work location and the X and Y, there might be many people who have the same characteristics and going to the same home work location. So in that sense, there might be many people in the data, many rows which are similar, but they are not like, but that's possible in the HTS data as well at a sum aggregation level.
But you're not like
No.
measuring me twice?
No. These are unique based on the, I mean, we can see that from the common distribution of the Y variable of the HTS and PC, it's quite similar. So that also gave us a bit of confidence that maybe these two data sets are not super different in terms of how they look like. So what we do is we generate the population at the different level, and let's say we generate the 3 million population, and we see the number of generated attribute combinations which are not there in the HTS data, right? So you will automatically generate a lot of household travel, home and work locations which are not there in the HTS data. And we actually generate around 10 to the power 6 new home work locations, which is not unexpected. But if you look at the number of unobserved let's say you generate the 3 million, out of that you find that 2.1 million people do not have the attribute combinations which are observed in the HTS data. So you are sort of generating the 2.1 billion new agents out of these 3 millions while you are combining the HTS and the PC data. But remember, we are considering the home and work location as an attribute, and that is what is mainly creating these such high number of new attribute combinations. But I think the positive side of looking at it is that only 0.3% of the sample size is able to present the 30% of the individuals in the synthetic population. So that's I think a positive side of looking at it. Now I would present some results to show the linear combination part when we generated the data. So what we did is, for the home location, we presented the distribution from the fusion and the HTS data. This is the home location distribution, and this is the fusion versus PC data. And you can see the orange color is positive and the blue color is negative. So if you look at these two differences, if this is negative, this is orange, then this is blue on the, if you look at the difference between these two. So basically we always generate somewhere in between the HTS data and the PC data, these home and work locations. And similarly, for the housing type, we check the marginal distributions for these are the X variables, which are specific to HTS data. We are able to do quite well in terms of generating the X level data, as well as the one thing to note here is the common attributes, how they were generated. So it's not super apparent, but let me look at this plot. If you look at this plot, you have the red one, which is the HTS data, and this, I would say, dark green is PC data, and fusion is somewhere in between. So because the differences were not so significant between the HTS and PC data in our case, this averaging effect, the linear combination effect is not very clear, but you will see that this data fusion is always somewhere in between these dark red line and this middle line. So this is reflected in the results as well when we did it. So few more things, we wanted to see few more properties of what happens as you increase the number of clusters, because this is very important to see. So we tried some extreme cases when alpha equal to 1 and alpha equal to 0. So when we look at some extreme cases, when alpha equal to 1 and k equal to 1, and at the same time, when you look at the alpha equal to 0 and k equal to 1, one thing that you will see, that when k equal to 1, that means there is no clustering happening. The fused distribution, in the fused distribution, the xi, when we condition on that, we don't have any z here. So we lose the relationship between the xi and z when we have the k equal to 1. And when we have the k equal to h, which is number of clusters equal to the number of household, number of HTS data points, then in that case we get the full conditionality of the zh when we are deriving the xi distribution, and that is in the fused distribution. So these are in extreme cases, in the boundary condition cases, we are able to derive these things, but we see that the correlation still exists for the less extreme situations as well. So we looked at how increasing the cluster also affect the distances of the JS distance, the JS term for the HTS data and the JS term for the PC data. So one thing to note is the JS term is not affected by in the PC data, right? Because in the JS term in the PC data only depends on the YZ and the ZH combination, which is not much affected by the number of clusters as such. So we have seen that the DJS term is not affected for the PC is not affected by the clusters, but for the HTS it does, irrespective of the value of alpha. Because even if you have alpha equal to 0, when you are not using the Y and the Z from the HTS data, you are still using the X from the HTS data. So even alpha equal to 0, this number of clusters affect the DJS HTS term. Okay, so just to summarize, it's as Khan asked, it is not a parametric method. We don't put any distribution. We directly learn the probability masses. So it's a non-parametric method that can deal with high dimensionality of the spatial attributes, and it ensures the feasibility. We are not generating any attribute combinations which are not there in the data sets. And it tried to create the harmony between these two data sets. Obviously, it's a very first step. We have some ideas to improve it further, but yes, still it is just a very first stage to really combine these two data sets together, because the methods that we have seen in the literature are mostly simulation-based methods, not very analytical methods, so that we can at least see the properties of the fused distribution. So that was the motivation to develop, to apply this from more analytical way. Okay, so how much time do we have really? I think it's almost there, so I think I'll not go into the third part, but I'll just in 3 minutes. So this is the working draft of the paper. I'll share the slides with you as well. And you have a question?
For the PC data, is it also sampled to be a representative sample of the
No,
population?
it's just the raw data that we directly get from them. So
Because in the graph that you have the share of age and different things, it seems to be very similar.
yeah, but this is coincident. We haven't done anything with that.
And about the first part, are the models transferable, or should we tune the hyperparameters for each population?
I think they should be tuned for each population. Yeah, we can't transfer them.
So once you have generated your synthetic population, which is the fusion of the two previous data sets, how do you go about validating that?
So first we need to understand what do we mean by the validation, right? So if you think about the validation, there are two things, right? And this is sort of a validation exercise if you think about it. This is not the validation, but let's look at the previous slide. So what we are saying is, whatever you are generating, is it there in the PC data or in the HTS data? So we can show that either it is a linear combination of the HTS and PC data, or it is in the HTS data. So if it is just the X distribution, so if you think about the next part, this is sort of a validation. If you look at the first part, that we are able to preserve, this is in the fused data and this is in the HTS data. So this is the distribution in the HTS data and this is the distribution in the fused data. So both are matching basically. So we are preserving the marginal distributions of the HTS data. You can draw these things for the joint distributions as well, and you can see if they are preserved or not. But I don't think there is any other way to validate it. Yes.
I saw the work of location relations of HTS and PC data. I find a quite different commuting pattern.
Mm-hmm.
For example, the HTS has a clear diagonal, which shows a good Jobs-Housing balance.
So based on our understanding of the data, we also thought that is there anything specific going on there? But it's just that they have defined the numbering of those home and work locations. What you see, 1 to 400 is just the numbering of the home and work locations. Yeah, so there is no meaning of that straight line that you are seeing in the specific area. Really. Yeah, but it's like, yeah.
The straight diagonal says the job home location and work location located in the same.
Yeah, closely.
So the commuting distance will be quite short, right?
Yes.
But in the PC data, it shows a quite diverse matrix.
I see what you are saying. Yeah, at least that diagonal line says that in the HTS data, at least we see more people have the closer work location.
Yeah,
right?
which means the Jobs-Housing
Yeah.
balance is
That's
great. So my point is, how do you, what's your attitude to this difference between HTS data and PC data? Because when I'm using PC data in China, a critical point is that I need to validate it's close to HTS data.
So I mean, it's interesting that in the commuting distance, it is not reflecting the differences. So ideally, I was hoping to see the differences in the commuting distance distribution if those differences are there in the home and work locations. But when we are aggregating the data, we are not able to see those differences at least. The possible reason can be that I'm not sure at this moment what can be the possible reason that the closeness that we are seeing in the location index and for the home and work here, that is not reflecting in the commuting distance. So I think I can double check and see why is it not reflecting in the commuting distance. So this can be a one way to check whether your data is similar or not in terms of the commuting distance. But apart from that, I mean, the other way is you can get the third data set, which is maybe the smart card data, and you can try to validate using that third data. So initial our thought was we will generate the synthetic population using the HTS data and let's say cell phone data, and we will validate it with the smart card data, because smart card data also help you in inferring the home and work locations of at least transit riders. So that can be one way to sort of validate it using the third data, if you want to think about the, maybe one way to validate the value of alpha is like we bring the third data in the picture and we try to pin down the value of alpha, which helps us in showing something which is available.
Because the PC data has some noise, so it might increase the number of infeasible samples that you mentioned. So it's, I saw you have a question that parameter alpha to determine whether we depend on the TS data and whether we depend on PC data. But within the PC data, is there any parameters that consider which kind of samples are reliable and which of them are not reliable?
So at least in this research, we haven't thought about that part, that how do we check the feasibility or the, I would say the distribution of the PC data is correct or not. We just use the alpha parameter and let the modeler decide how much weight the modeler wants to put on the HTS data and PC data. But this is, I think, a very good question to think about, and at this moment or even earlier when we thought about it, we mainly thought about the third data set to bring in, but I don't have any analytical ways to think about this problem at this moment. But if you have any analytical ways to think about it, we can discuss it afterward as well.
Thinking maybe your cluster-based method can deal with that. Because you have shown that some clusters exist in HTS and not in PC.
We have solved that problem in the recent work, so we don't have that problem now. Now in the new work, we have ensured that the clusters that are in HTS data also are very much distributed. So that is not a big problem. That is not a hurdle in terms of handling this issue. But maybe we talk more about it. You have a question?
What's the range of runtime in terms of both sample
Yes.
size and number of attributes?
Yeah, so in this, running this whole optimization problem was around 3 to 4 hours on a regular computer, but it can be parallelized very easily because all these problems are easily, embarrassingly parallel. So runtime is not a problem because the problem is breakdown into the simpler problems. Okay, so I will use this time to maybe briefly show you a little bit of advertising, I would say. So I'll share this presentation and as well with you. This is something which I haven't covered, the third topic. But this is our LinkedIn page if you want to follow, but I'll show you the lab facility video. So we also work on the individual level behavioral science part. This is more of a system level part. And individual level, we work with combining the cognitive psychology with the economics, and we calibrate the models using the process data, such as the eye tracking and the brain data. So we are doing many things related to that. So let me show you what facilities do we have in our lab, if this video works.
Prateek, maybe you want to say a little bit more about the brain imaging and eye tracking.
Right. So I'll just say after this. So yeah, we are working with yeah, so mainly we are working on the sequential sampling models from cognitive psychology because sequential sampling models actually have the way to model the information search process or the evidence accumulation process of the decision maker. So it provides a structural way to understand how people are accumulating information. And when you have the already structure in place, it is easy to modify that structure using the information data itself. So that's the main reason we are moving from the traditional discrete choice models and going to the cognitive psychology, and we are able to show some interesting effects that can be captured by the sequential sampling models, which cannot be captured by the traditional discrete choice models. For example, you might have gone, when you go to Starbucks, you have the small coffee and the large coffee, and you have the medium coffee as well. Medium coffee has a very little difference in price, but significant difference in price, in the quantity, right? So the medium coffee is sitting there as a decoy to increase the preference for the large coffee. So they don't want to sell the medium coffee. Medium coffee is nudging you to increase the preference for the large coffee. So we have done some similar experiment with the ride-hailing drivers. We asked them about their current rented vehicle. In Singapore, it is very difficult to buy a vehicle, so people rent. So, and we gave them an electric vehicle. And we made the electric vehicle equally attractive to their conventional vehicle. They made it basically on their own. And then we introduced the decoy electric vehicle to them, which has the very small differences in the price, the rental price, but the significantly lower driving range. And we have seen that the decoy can actually increase the preference for their target EV that we want to sell. So we have, and the point is these sequential sampling models can explain the effect of the decoy on the preferences, which cannot be explained by random utility maximization models. So we show that in the paper, and then we show that how you can use the parameters of the model to design the decoy, the effective decoy alternative. Because how much should you reduce the driving range so that the effect of the decoy on the preference of the target alternative is the highest. So this is also shown in the paper. So this is how we show the value of sequential sampling models over the discrete choice, traditional discrete choice models.
Is the use of a decoy to nudge the behavior of a seemingly unknowing participant ethical?
Okay, so I think there is no harm. I don't think that it's unethical because some psychologists call humans predictably irrational, right? So these companies are kind of understanding your irrational behavior. They are able to predict your irrational behavior, and they're just utilizing it to make their business. They are not insisting you to buy the medium coffee, right? Or they're not insisting you to buy the large coffee. So I think it's fair. It's fair. It's just us who are not able to understand the trap, basically. That's my understanding, but I mean, you might have different opinion. Yeah. And if you are interested, one more thing we are doing, which is very, very interesting, is with the EEG brain data. So I think the big problem in the autonomous vehicle world right now is in the difficult situations, whom should autonomous vehicle hit, right? If let's say there are two pedestrians and one is the kid, other is the male or female, a young male or female, I mean, what should autonomous vehicle do it has only chance to save one of them. So we feel like there are two ways to approach this problem. First is what people think in the society, because it's a dilemma, it's a trolley problem, right? So what we did is, there is a very well-known Nature paper on that, what are the biases in the society towards the specific demographic groups. So we did an experiment in our lab where we allowed the autonomous vehicle to come from the front, and the two pedestrians are coming from both sides. We vary the age and gender of two pedestrians, and the respondent can decide which pedestrian to actually save. As like a male, young over child, male, or etc., many attribute combinations. And we collect the brain data while they make this decision, basically. And we are able to show that the brain data can explain the biases that people have in the choices. So this is the initial results that we have. We are working on the draft for this paper. So this is how, and we connect these brain data with these sequential sampling models, and we show that the sum of the parameters of these models mimic what brain data is showing. So there are some evidence in the literature that these sequential sampling models have some cognitive underpinning, and we see that also in our research about the trolley problem and how the socially acceptable decisions should be made. So yeah, these are some other things that we are working on. If you go to the LinkedIn, I think many working papers are going to come in next 1 year. Thank you.
So what's the goal? So you take people from the same background and then see if their brain waves are the same, or?
So the motivation is as follows. So with the brain data, what we can identify the decision-making process, right? That whether they are thinking from an emotional perspective, we are thinking from the rational perspective, or they are using a different decision rule. So what we can do is, we can't collect the brain data for too many people, but let's say in the lab, we collect the brain data of 300 people. And we try to manage enough demographic variation in the lab. We can do the same experiment in the image settings, image-based experiment or the video-based experiment outside the lab when we don't collect the brain data. So again, the idea is, and then we learn some mapping between the demographics and the attitudes with the brain data that can help us in understanding the decision-making process. We transfer that mapping to the out of the lab data, so then we can figure out that what is the decision-making process of those out of the lab data. And from that, we can kind of figure out the probabilities that at least on a population level, people want to put an autonomous vehicle to save one respondent over another. So we are making the predictive model where we have the good decision, we have a latent classes with an appropriate decision rules. So let's say the output of this model can be that if there is a male and female and a young and one of them is young, other is child, then your model can predict that there's a 0.8 chance and the 0.2 chance. This is what average population wants, basically.
So you want to make the autonomous vehicle decision acceptable
to the society. But if people don't want that, let's say we can make it a transparent phenomena, that let's say this is what is happening. The other way to think about this problem is, we don't want it to be biased. We want it 0.5, 0.5. Then this model can tell us how far we are from the socially acceptable decisions. So if we don't want to implement what we are getting through this model, we at least know how far we are from the acceptable decision, and then maybe we can nudge the people to what government want to implement in the end. That's one way to think about it as well.
But when you make that experiment, you make an assumption that people make the decisions based on, in this case, age and gender.
Yes, but we need to replicate this experiment in many other situations, number of people as well, because it matters whether there are one person versus two people. As of now, we have considered a bit simplistic situations to test the concept whether there is something there which is interesting or not. One thing also, we found that in the image-based experiment, we don't see the differences in the choice biases of the male and female respondents, but in the video-based experiments, we see the biases in the preferences of the male and female. and we try to explain why those biases are happening in the video.
What is the difference? So male kills male and
So in the image-based experiment, male and female both prefers to save female more, around 0.65 and 0.35 probability difference. In the video-based experiments, females even wants to save females more, like 0.8, 0.2 probability, but the male probability decrease, and male wants females to save 0.6 and 0.4. The probability.
males are more fair.
That's, I think, audience to decide. So yeah, this is still, I think we are writing the first draft, but we are thinking of doing more experiments and coming up with more interesting ideas. How do we use the brain data? Because the problem with the brain data is unlike eye tracking data, if you look at the single trial brain data, it's not very useful. You have to aggregate this information over 30 to 40 trials, then only you can get rid of the noise and get some interesting information. So it's not super easy to incorporate that brain data at a choice situation level models. You can do it at a respondent level, but at an experiment level, it's very difficult to incorporate because of the high noise in the EEG data. So we are still looking at neuroscience literature and understanding.
There's a very large group at NYU which is kind of pioneered this kind of economics. So they work with animal models like chimpanzees and but also humans.
I see.
I can give you their link. I mean they're kind of very well known. So animal models are different because they kind of open the head of the animal with sensors.
Right.
But for human, I think they do this kind of work for economics.
Right. So we have a research fellow in our group who worked on the EEG on the mouses. So now he's interested in humans more than mouses. So we have the neuroscientist as well in all that.
Yes.
So it will be good to know the other people. The thing I've seen is that the way we use the EEG data in the behavioral models is a bit different than it is used in the biology or the
So these guys were actually very concerned about economic decisions.
Okay.
You know?
Oh, okay.
So
I
basically,
see.
like how people respond to different incentives.
I see.
Of course, they use surrogates for animals,
Right.
whatever food,
I see.
whatever. So and then they try to kind of map that to human decisions about economics.
So that's interesting. If they are working with the economic decisions, then it's very transferable.
Definitely,
Yeah.
even like they were working on route finding,
Oh, okay.
things like that. So.
Interesting.
Yeah, because when I first came to NYU, we had a large kind of, how do you call it, a one-day workshop with Cowley Foundation. Cowley Foundation is mainly into this neuroscience type of thing, but the idea was to move to economic decisions. And these guys, there's a group of people working on that. So I'll share it with you.
Yeah, that will be great. Yes, thank you. So I will be available for talking and chatting and discussing new ideas after the talk.
Yeah, feel free to talk to Prateek. I think Daniel was talking to. So thank you very much for great presentation. We learned a lot.
Thank you.
And hope you come back.